Hello everyone, welcome to another video. Today's video is going to be a bit of a combination between maths and physics, and I'm going to be going over with you a differential equation called Newton's law of cooling. And this equation is reasonably famous, and when students learn differential equations for the first time, it's usually one of the first examples they get treated to. So I'm going to pose the question here. What is a differential equation? If you're someone taking maths IGCSE or further pure maths IGCSE, the concept will probably not have been introduced to you just yet. You will have learned about related rates problems, or at least you're going to learn about them, and that's a sort of step below differential equations, because in related rates you start with something in the world of first differentials like dA by dt of some shape, and you need to find dr by dt at a particular a, or something along those lines. This kind of related rates problem is quite frequent in the math IGCSEs, but it is, as I say, one step below a differential equation problem. And a differential equation problem would be something like, you know that y is equal to dy by dx. Please solve for possible values of y in terms of x. So what functions could y be? Well, the answer to this one is e to the x, because you know it differentiates to itself, but there are more sophisticated ways of going about this than just guessing. And I'm going to introduce to you the sort of concept of having a differential equation where you have both the function and its differential in the same equation, and you're trying to find the function. I'm going to introduce that way of thinking to you, and hopefully get you guys to experience some of the math that you'll be seeing further on. And if possible, follow along, because I will try to keep this as accessible as possible to students who have not yet touched a single differential equation before. Or basically, I'm going to assume you have the knowledge of a reasonable IGCSE for the pure maths student. So, as in the title, the differential equation we're going to be looking at is Newton's law of cooling, and it basically states that the rate of change of temperature, the differential of temperature capital T with respect to time lowercase t, is proportional to the difference between the temperature of that body, T, and the temperature of the surrounding environment. So in math terms, if we wanted to get rid of this proportionality sign, which is a sort of physics artifact, then we'd say dt by dt is equal to kt minus t environment. And what I'm actually going to do here is replace capital T for temperature with theta, because theta is also a value that's a variable that's used to represent temperature, but when I read out what I'm writing and when I'm explaining, it will be clearer for me to say theta and t instead of uppercase T and lowercase t. So d theta by dt is equal to k times theta minus theta env. And here env stands for environment, temperature of the environment, and this theta is the temperature of the body in question, which is also the same as this theta. Alright, so oh, and finally I want to make the point that this k is necessarily negative, because if you think about it, if you have a hot thing, so for example a human, in a cold environment like Antarctica, then of course, because this difference in temperatures is positive, that doesn't mean the temperature of the human is still going up. No, 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 no. in the physics sense, you've got to think about how the human is constantly losing body heat to the surrounding Antarctic environment. And as the temperature gap gets wider, the human loses body heat faster. So, of course, this d theta by dt, this constant of proportionality would be negative here. Anyways, let's get down to some math. So how might we think about this? Well, we're first going to try and solve it in the abstract case, or generalized case. And that basically means valid for any sort of situation. I'm going to call this minus k for making it clear that k is a negative, this constant is negative. d theta by dt is equal to minus k theta minus theta ENV, or the temperature of the environment. How would we go about solving this? Well, if you looked in the title, I did mention one of the things we're going to need to keep in mind here is that basically the integral sign, which represents a continuous sum, because you can see it's a kind of misformed S, or rather a different font of S. Well, fun fact, English S's in medieval times, like medieval writing, some people wrote S like this, and some like this. So that's kind of where the integral sign comes from. I'm not particularly sure in what historical age that was the case, but I know it was the case for some period of time in English history, which is why we get this integral sign. And there's quite a lot of story behind this sign as well, because it's different, I believe, in Russia, as well as either in another European country from England or America. Anyways, this integral sign is separate to the infinitesimal change in the variable. As a reminder, this lowercase d represents infinitesimal change. This is a topic that I've covered several times on my channel because I believe it's very core to understanding calculus, and it unfortunately isn't taught very well often. But anyway, if you would like to find out more about that, or if my explanation is unclear in this video, please head over to my video, what does dy by dx even mean? Or what's the meaning of sdx, sy dx, for more information on that, or you can just ask me a question in the comments, or at my email, watchmedomath@gmail.com. So this is a separate term to this. This is an operator that you can apply to something which is multiplied by an infinitesimal change. This can only exist when the term it's being applied to involves an infinitesimal change, generally speaking. However, they do not come as one group just because of notation. They come as one group because this is summing up an infinite number of things, and this is an infinitely small thing. The integral sign is a continuous sum of an infinite number of small things, and the dx term multiplied by everything inside of the integral makes the value of this mathematically zero, basically, for lack of a more precise explanation, which is why you can have equations which are like dx is equal to dy. For instance, if dy over dx is equal to 1, then dy is equal to dx. And while this is just saying 0 is equal to 0, I personally would argue that there is more information contained within dy is equal to dx than 0 is equal to 0, because of how it relates the two variables. But in a purely mathematical sense, you can't really do this, but it is done in physics and in maths because it is a convenient and consistent explanation for this d, this lowercase d here. So, with this explanation out of the way, I'm going to show you how we might solve this kind of differential equation. So, there are a couple things that you can do. And one of them is, if we take this, we have this information here. What can we do with it to find a function theta? So theta here is a function of time. Let's remember that. So what would we do here? Well, one thing we could try is to multiply both sides by dt. This will not work. It's not a valid way to get to the answer, but I want to do it for the purpose of explanation. So let's move over here. If d theta by dt, the rate of change of temperature of the body, is equal to minus k times the temperature, which is a function of time, theta t. So d is more like d theta t over dt. So equal to minus k theta t minus the temperature of the environment, which is a constant. And we multiply both sides by dt, the infinitesimal change in time. We get delta theta t is equal to minus k times theta t minus theta environment with respect to time. So now that we have this infinitesimal term, which is basically 0 on one side, this infinitesimal term which is basically 0 on the other side because of this dt and this d theta, then what we can do is integrate both sides. And by integrate, I do not mean put this with a dx. No, no, no. I just mean to use the continuous sum, applying the continuous sum as a sort of operator like sine, cos, tan, d dx. We're applying this as a sort of operator to d theta t and this term times dt. So we get the integral of 1 with respect to theta is equal to minus k, taking the constant out, times the integral of theta, the temperature, minus theta and the temperature in the environment with respect to time. And so on the left side, we have something fairly simple. This obviously goes up to theta t plus c because it's an indefinite integral and there's nothing inside the integral. It's just like how the integral of dx is equal to x because you're summing up all the infinitesimal changes in x. So this becomes theta t plus c on this side, and this is equal to minus k times, well, the integral of theta t with respect to t minus theta environment times t plus c. And this comes from the integral of minus theta env with respect to time, where theta env, the temperature of the environment, is constant. So now we have a bit of a quandary, we have a bit of a problem. We have this term, the integral of theta t with respect to time, which is not going to go away because we have no information to sort of decipher what this term is. So we need to find another approach. How might we go about that? Well, as I mentioned earlier, we are dealing with d theta and dt. So one way that we could deal with this equation is, instead of just leaving it in the form d theta is equal to this times dt, we could actually manipulate this equation until we get some function of theta on one side and some function of time, or just a constant term, on the other side. that would allow us to finally integrate both things, and in doing so, get us to a solution. So what might we do? Well, I'm going to clear the board for us so that we can get back into a clearer frame of thinking. We have d theta by dt is equal to minus k times theta minus theta environment. And multiplying both sides by the infinitesimal change in T dt, we get d theta, the infinitesimal change in the temperature over an infinitesimal change in time, is equal to minus k times, where k is some positive constant, times the temperature itself minus the temperature of the environment, so the difference in the temperatures of the body and its environment, multiplied by the infinitesimal change in time. And what I'm going to do here now is divide both sides by this term, theta minus theta environment. So d theta times 1 over theta minus theta environment, or I'm just going to write theta e from now on for simplicity, is equal to minus k, the constant, times the infinitesimal change in time. And if you're a bit lost, if you're a year 11 student watching this and you're a bit lost, that's completely okay, because this is something that in theory is possible at your level, and you may want to slow the video down and try and follow along, or if that doesn't work out, then it's absolutely okay, because you can just leave a question in the comments and I can help you. But we just need to remember at every step in the road that this equation represents a sort of physics rule that we know, and this d theta is, for instance, on a graph of temperature against time, cooling, like a human cooling down in Antarctica. This d theta is just some infinitesimal change in the temperature over some infinitesimal change in time. These two quantities, although zero, actually have a physical representation, and this is what relates them together. And we are trying to go from this, how this and this are related, to an actual equation of theta over time. So let's get back to the mathematics. What we can do now here is, because we've got some function in terms of theta, so this is like 1 over x minus k dx. Basically, this is what we've got here, just in terms of theta, because that's our quantity for temperature. What we can do now is apply the integral operator, like this continuous sum symbol, to all of the 1 over theta minus theta e times d theta little pieces, which will be equal to the integral operator applied over minus k dt, because if this and this are the same, then if you integrate them, it must work out, basically, is equal to minus k times the integral of dt, the infinitesimal change in time. And this minus k is just being moved out of the integral because it's a constant and we don't want to deal with it. We get the integral of 1 over theta minus theta e, where theta is our actual variable and theta e is a constant, d theta, is equal to minus k times the integral of 1 with respect to time, or the sum of all the tiny time pieces in the graph. So to make the big actual time, we need to sum up all the tiny dt's along the graph. I hope that makes some visual sense as to why it works, but anyway, we have the result, minus k t, and then plus c because it's an indefinite integral. I forgot the plus c when I was doing the fake example earlier, so please forgive me, that's an unforgivable sin. I should be shot at dawn for doing that, but anyway. We have a harder integral over here, which is basically in this form I write earlier, 1 over x minus k dx, or 1 over theta minus theta e d theta. So what we're going to have to use here is the rule that basically the integral of 1 over x with respect to x is equal to ln of the absolute value x. And this is something that really it deserves a video of its own to go over. And if you would like to pursue investigating why that is yourself, then I recommend that you start with y is equal to ln x. E to the power of y is equal to x. Let u be e to the y. And finally find d e to the y by, oh, don't bother with this step. Find d e to the y by dy times dy by dx is equal to dx by dx. In finding this, you can sort of, it's kind of like applying the chain rule. It's called implicit differentiation, when you basically you differentiate in terms of whatever you like, and then you add the dy by dx to the outside to get it back in terms of x, because you're doing this essentially. This is not a very clear explanation at all, and like I say, this integral deserves a video of its own. If you would like to see that video, leave a comment in the description. And so we're gonna take this as gospel basically. And this integral results in ln of theta minus theta e plus c. This is a sort of a special case that I'm not sure if they teach you in the new 9-to-1 syllabus. They didn't teach it to you in the previous one. I saw no reason that they wouldn't, because it's just another thing to remember by their standards. But anyway, integrating this, you get the ln of theta minus theta e plus c is equal to minus kt plus c. And what we can do here is expand this bracket out. Ln theta minus theta e is equal to minus kt plus kc. Well, this is just a constant, so we can replace it with another c. And this c has been moved to the other side and combined with this c already. We take e to the both sides. E to the ln theta minus theta e is equal to minus kt, or e to the minus kt plus c. And of course, when you have e to the something plus something is equal to e to the first thing times e to the second thing. So e to the c being a constant, we'll just call it a, because that's what you usually call constants that come out of e to the c. A times e to the minus kt is equal to, on this side, theta minus theta e. And finally, we get theta is equal to a e to the minus kt plus theta e. And this actually turns out to be a pretty cool graph. So if you were in Antarctica, everything around you is ice at 0 degrees. Antarctica is colder than that, but just for the sake of argument. And you're a 37-degree human body. Then your temperature is going to be some constant times e to the minus kt plus 0 degrees. And the choice of degrees Celsius for the units of temperature is kind of arbitrary, because this is positive 273.15 Kelvin, our actual unit of temperature, but because we're only looking at the difference in temperature between the body and the environment, the absolute unit doesn't matter too much, because we're kind of looking at this from a mathematical perspective and not a physics perspective so much. And the way you would get from a solution like this to your actual function is that you need some particular data. So say you knew that you left your fried rice out in Antarctica. It was 50 degrees when you left it. You went to the toilet or something. And at that point, T was 0. And you came back from using the toilet 2 minutes later, and it was 20 degrees. Absolute nightmare. What do? Well, because it's an exponentially decreasing function, you basically know that it will decrease by a factor, or it will be scaled by a factor of 0.4 every 2 minutes. And what does this actually mean? Well, that means that you can take this function and put it in the form theta is equal to 50 times 0.4 to the, well, 2 minutes is our time interval, so t over 2 minutes plus 0 degrees Celsius. And while that's one form, that's sort of the practical form from the actual data that you might use, because the information that this differential equation has given us is that it's an exponential decay of temperature, basically. But if you wanted to put it into a e to the kt form, well, a would be 50, because if 50 is when t is equal to 0, that means minus kt is 0, e to the 0 is 1, and plus 0 degrees Celsius. So that means a would be 50, and with additional data, say 20 is a e to, or 50 times e to the minus 120 k plus 0, you'd get 2 over 5 is equal to e to the minus 120k, or taking the ln of both sides and multiplying by 120, minus 120 ln, or 1 over minus 120 ln 2 over 5 is equal to k. And that's sort of your explicit function for temperature based off some real data and doing this load of calculus that I've sort of half walked you through. I apologize that this video was not perhaps not as good at explaining as I usually am, because this is a difficult concept to get across in the terms of Year 11 mathematics, so I've really tried my best here. The key point to remember is basically that when you first learn differential equations, just think of it as a step up from related rates. You've played with functions in the sort of real world, the y world, the y and x world, and related rates you play with things in the d something world. So like you're playing with differentials, dy over dx, dA over dB. You're playing with those kind of ratios between infinitesimal changes d theta, dt, dx, dy, dA, dB. And differential equations is the next step up of that, because you are actually allowing yourself to separate out the fractions and hop between the two worlds of differentials and sort of quote-unquote real-life functions. And when you get those real-life functions, there are many possibilities as to what they could be to satisfy a particular differential equation, and oftentimes you might have to find out the answer by looking at actual real data, which is why this is kind of a maths and physics crossover video. I hope that clears it up for people who weren't so clear watching all the math all the way to the end. If you did, many thanks to you, because you're helping support the channel. And I'm not going to be producing as long of content in the coming weeks due to personal things and schoolwork, basically. But I will maintain my upload schedule. There will just be shorter videos or less in-depth, basically. But I hope to continue nonetheless. So if you haven't subscribed already, please subscribe to the channel, and thank you for watching.